So hello students, welcome you all to the next lecture, that is lecture 9. So today in this lecture we'll be discussing about the transistor biasing. Though we had discussed it in the previous lecture in lecture 8, but that was not enough. We have to go more into the details of the transistor biasing. So let's begin the lecture. As we have discussed about the transistor biasing in the previous class in lecture 8, today we'll be going more into the details. So moving on to the first topic, that is the operating point. So what is the operating point? By definition, it is clear that as it is mentioned here, it is obtained from the values of IC or VCE voltages when no signal is given to the input. Therefore, it is also called operating Q point or the question point because the variations of IC, that is the collector current, and VCE, the collector emitter voltage, takes place around this point when no signal is given. As there is no signal present, the operating point is called the silent point or the question point. That's why it's named as Q point. It is a point on IC-VC characteristics. As you could see here, the IC-VC characteristics in the left hand corner, where the transistor is silent, that is no input signal is given. The operating point can be easily obtained by the DC load line method. Here the DC load line is being explained. By this method, the operating point of particular base circuit current IB, the purple line, according to the load line condition. The OA, the line OA is equals to VCE, which is also equals to the VCC. VC is the collector emitter voltage, the voltage across the collector and the emitter, which is equals to the VCC, that is the collector voltage. That's in the other hand, OB, the line OB, which is equals to the current IC, which is equals to VCC divided by RC. OD in milliamperes, the line OD, and VCE is equals to OC, the line OC in volts. The position of the Q point depends on the applications of the transistor. If the transistor is used as a switch, then for open switch the Q point is in the cutoff region, and for the closed switch the Q point is in the saturation region. So the Q point lies in the middle of the line of the transistor, which operates as an amplifier. It is to be noted that there are two conditions. The first one is the saturation region and the other one is the cutoff region. So in saturation region, both the collector base region and the emitter base region are in forward bias condition, that is heavy current flow is present, and the other region where both the collector base and the emitter base region is in reverse bias condition is called the cutoff region. So you should remember that there are two regions. First one is the saturation region and the second one is the cutoff region. These two conditions happen when the collector base and the emitter base are in forward bias condition, else both are in the reverse bias condition. Now moving on to the factors affecting the operating point. So there are many factors which affect the operating point, but the most prominent one is temperature. Here the temperature is affected in this manner that the current ICBO, that is the current to the collector base current, gets doubled for every 10 degree rise in temperature, 10 degree centigrade rise in temperature, and the voltage VBE, that is the voltage across the base and the emitter region, decreases by 2.5 millivolts for every 1 degree rise in temperature. So this is the relation between the temperature with the current and the voltage. Now So the main problem which affects the operating point is temperature. Hence, operating point should be made independent of the temperature so as to achieve the stability. So to achieve this stability, biasing circuits are introduced. So let us move on to the process of stabilization. So what is stabilization? It is the process of making the operating point independent of temperature changes or variations in parameters, as we if we go by definition. Once the stabilization is achieved, the values of IC and the VCE become independent of temperature variation or replacement of resistor. So a good biasing circuit helps in the stabilization of operating point. So if the transistor is stabilized, then these two, the VCE and the IC, both these are independent of temperature. So what is the need of stabilization? Why do we stabilize? First one, as we discussed, temperature dependence of IC. So the second one is individual variation, and the third one is thermal runaway. So let us discuss these three terms in details. First one, temperature dependence of IC. If we look at this formula which states that IC equals to beta IB plus ICEO, then we could say that it is also equals to beta IB plus beta plus 1 ICBO, where the collector leakage current ICBO, that is the base emitter collector current, is greatly influenced by temperature variations. To come out of this, the biasing conditions are set so that zero signal current, that is IC equals to 1 milliampere. Therefore, the operating point needs to be stabilized. That is, it is necessary to keep the current IC, this value, as constant. The collector current should be constant. Therefore, there is a need of stabilization in case of temperature dependence. Now moving on to the next, which is individual variation. So as the value of beta is the constant which decides the IC and the IB value, the relation between the IC and the IB value. So as the value of beta and the value of VB is the base emitter voltage, are not same for every transistor. Whenever as the value of beta and the VBE are not same for every transistor, whenever a transistor is replaced, the operating point tends to change. So in a circuit, if we have a transistor and we replace it with another transistor, as beta and the VBE values are different, so it is the operating points also tends to change. Hence, it is necessary to stabilize the operating point. Now moving on to thermal runaway. So what is thermal runaway? By definition, the self-destruction of such an unstabilized transistor is known as thermal runaway. As the flow of collector current and also the collector leakage current causes heat dissipation, if the operating point is not stabilized, there occurs a cumulative effect which increases this heat dissipation. So in order to avoid this heat dissipation, or to avoid this thermal runaway and the destruction of transistor, it is necessary to stabilize the operating point and to keep this value IC as constant. As you could have experienced in your lab, that when if you use in your basic electronics or analog electronics lab, if you use a transistor for a long run, it gets heated when high value of voltage is given to the transistor, and with that very high heat the transistor gets destroyed. So these two equations can be analyzed again to sort out that thermal runaway is a condition which can destroy the transistor. Now moving on to the next topic, which is stability factor. So by definition, the rate of change of collector current with respect to the leakage current at constant beta and base current is called the stability factor. It is understood that IC should be kept constant in spite of variations of ICBO or ICO. So the extent to which a biasing circuit is successful in maintaining this is measured by stability factor, and the stability factor is denoted by S, which is equals to the change in IC divided by change in ICO, that is the derivative of IC divided by the derivative of ICO at constant IB and beta value. So by differentiating these two values, this expression with respect to IC, we have 1 equals to beta whole into div divided by dic plus whole into beta plus 1 dico by dic, where it can be given as 1 equals to beta dib divided by dic plus beta plus 1 by s. Since this value 1 by s equals to dico by dic, it can be stated that S equals to beta plus 1 divided by 1 minus beta whole into dib divided by dic, where beta is the constant, the transistor's constant, and dib is the change in base current and dic is the change in collector current. Hence the stability factor depends on these three values. So guys, today we discussed the lecture 9. Let us discuss its key points, what we have discussed today in this lecture. First we discussed about the operating point, then we moved on to the factors affecting the operating point. Then we discussed about the stabilization process and what is the need for stabilization. Then we moved on to the stability factor, and then we concluded the lecture for today. So in the next lecture we'll be discussing about the introduction to the amplifiers. Then that would be our last lecture for this module 1. After that we'll be starting our module 2. Guys, if you find this video informative, please hit the like button and comment below if you have any doubts, and please subscribe the channel if you want to stay connected with us. Thank you.